Hi there, my name is Grant Imahara, and I'm one of the hosts of Discovery Channel's Mythbusters. I'm also an electrical engineer, a robot builder, and, oh yes, a former FIRST mentor. I'm here to talk to you today about the importance of design. Look, I know what the first season's like. It's intense. Everyone wants more time, right? Well, you don't get more time. No, you don't. But through design, you can make better use of the time that you have to be more efficient and get more done. Now I know it's tempting to just grab a piece of aluminum and start building the first thing that pops in your head. I know, I have. But this really only works for very simple challenges. And as we all know, FIRST is anything but simple. FIRST robots are, by nature, complex machines. In order to build them with the capabilities that you want, given the time that you have, requires careful thinking. The design process is your roadmap through this minefield. Seeing that journey and understanding the process of design is what this video is all about. Now you're saying, I already know all this, Grant. What's the difference? Well, the difference I'm suggesting is that you pay a little more attention to the very early stages of your design process. Now you're probably thinking, whoa, we do design. We draw it on a piece of paper or on a whiteboard and then we build it. Well, before charging forward to making parts, just take a little time to make a study model. It can be in the computer using CAD, computer-aided design, or it can be popsicle sticks and paper towel tubes. It doesn't matter what you use, as long as it helps you work out the problems. Because, let's face it, making a part over and over and over again is not only frustrating, but also very time-consuming. You know what I mean. You make a part, you test it, you take the assembly apart, put it on the drill press, drill a new hole just a little bit further, put it back together, rinse and repeat. In the end, you've got something that looks like a piece of Swiss cheese rather than a robot part. By using a model to test your ideas before making parts, you'll save materials and time. What? You don't believe me? It's already been done by many teams. I'll show you. Within FIRST, there are hundreds of instances of great design, but today we're going to focus on one notable example of excellent robot design. Team 111, Wildstang, and their lifting arm. This is their design story. Step 1, define. Understanding the problem. The challenge was to pick up an inner tube from the floor and lift it up 8 feet using a mechanism that was limited to an initial height of only 5 feet. Their design needed to be strong, lightweight, and controllable. These requirements and constraints defined the problem that they had to solve. The team started with a review of the required geometry, called a kinematic analysis. Basically, how small did the robot have to be to begin with, how long the arm had to extend, and the types of movements required. They used hand sketches to quickly identify the critical dimensions. Based on this analysis, they established that 2 linkages connected by rotational joints could accomplish this task. Step 2, ideate. Brainstorming. As a result of their discussions and brainstorming sessions, the team decided to model their robot arm on a human arm. The robot arm would rotate along 2 axes at its shoulder and along a single axis at its elbow. They decided to make each aspect of the arm analogous to a human's, with linkages as bones and power sources as muscles. Next, they had to build what they imagined. Step 3, create. Building. Team Wildstang used the CAD approach, building their arm in the virtual sense, in the computer. But as I mentioned, you can use whatever you want to make your models. They divided the arm into its major components, the shoulder, the upper arm, and the forearm/gripping system, and assigned each part to a different sub-team. These sub-teams worked independently to model their designs using CAD, and then put all the models together for testing. Early testing revealed that the original gripping system could hold a tube, which is good, but the tube rotated if you moved the arm too quickly, which is bad. Within the computer, they then easily moved around the pivot points until the arm had better range of motion and a stronger grip. The whole time they kept plugging away at the models to improve performance. See, they did all their testing in CAD and solved the problem virtually before any of the parts were actually made. Their computer corrections solved the real-world problems. Now that their virtual design was working great in the computer, it was time to make the parts and put the robot together. Step 4, solve. Manufacturing. Wildstang's CAD models not only helped them test the arm, but also served as detailed blueprints for fabricating the actual arm components. Each bearing, mounting hole, and attached part was precisely specified in the CAD model. This allowed them to make the final parts in one pass, saving materials and, more importantly, saving time. The result? Wildstang's arm had a full range of motion, was easy to control, and was strong. A phenomenal success. They used CAD to streamline their design process to keep them moving forward toward their goal. To review, make a model, work out your ideas, then make your parts. And like Team Wildstang, you can follow the same design path to efficiently create an elegant solution. And that, my friends, is what great design is all about. Or you can struggle through it the hard way. It's up to you. Either way, you better get started. Clock's ticking.